Okay, hi. So in this project, I'm going to just explain regarding how, yeah, so in this project, I'm going to explain regarding how did I solve the Coursera, basically this problem statement, okay? And so we are going to talk about this regression problem statement and my output, basically talking about these four things, okay? So, so what I do is I use an automatic machine learning framework. So I use this Google Colab, which is provided by Google. Uh, this has an inbuilt GPU and also a CPU, of course. But then it really takes care of all of the or easy installation of Python libraries. So I've used Python for this. But then I use an automatic machine learning framework called PyCaret. So it has a regression module because this is a regression problem since we were predicting a continuous value. So now, so this is an open source low code machine learning library in Python and it automates machine learning workflow. So you can actually experiment a lot of different models using PyCaret. Okay. So now what I do is I install a library called pandas. This is for so basically I try to import the data into my environment and then I kind of look at my data. Okay. Now then I check the PyCaret version I'm using. Now a typical workflow which I have actually used in solving this problem is I first have a setup of the environment, the PyCaret environment, and it's so once when I set up, it actually creates a new session and it actually installs a lot of different types of machine learning models. Then I run PyCaret on this data. I compare the model, I analyze the model, I find the model that has the best performance in terms of various performance metrics, and then using that best model I do the prediction and then I save it for my when the new data comes to do the prediction. So initially I create a session where which I call setup. So setup is nothing but I set up the PyCaret on and I set up it takes the input my data and the target variable. Target variable is the P which we are going to predict, and then once we do, it really it really does all this feature selection, feature engineering, and everything's on the data set. Okay, all the data pre-processing, normalization of data, everything. I don't need really to think about all this because if you see here, the scale of the data is different. So I can write my own code for doing different kind of feature engineering and normalizing the data. But then in the automatic machine learning framework, the advantage is it does everything for you. And then I what I do is I try to run, so basically this line will run a lot of models. So you can see these are all various regression based machine learning model like XGBoost, CatBoost, Light GBM, ridge regression, lasso regression. So all the different types of regression, and then it actually rearranges in ascending order from more accurate to. So basically if you see with lasso, uh, now, one of the advantages also is that you can see a lot of various metrics like mean absolute error, mean square error, and root mean square error, R square. So mean absolute percentage. So all of this metric you can have a glance of everything just at one stop dashboard, and you see the best performance is given by extreme gradient boosting on this data with the R square of 0.96 and MAE of 2.35, and then what we do is I try to look as analyze the residual, how the residual moves. Now from in the training and in the testing, it's quite the error is quite same, and that shows that the model performance is very consistent. Okay, and it also does a tenfold cross validation here. By default, it does a 10. You can change it, but I actually did a tenfold cross validation. And then you look at an error, how it looks like, the prediction error, and you can see uh, that's really it's trying to map it in a very proper way. So you can see the R square is quite consistent here. So this is the true versus predicted value. Then you can see next is which feature plays a very important role. So it found that this feature called 80, it plays a very important role. So this is the feature importance plot which shows for which feature played an important role in doing the final prediction. And then once you do that, you actually create a pipeline. You create different, basically you can kind of see various. So this currently this I think this there is an error here, but I think more importantly, this actually is because of the platform issue. It's not anything related to the code. But then you can always see various other parameters like which hyperparameters, how the hyperparameter optimization is done, and then how the feature selection is done, the feature importance, and everything here you can see. And then you take the best model, which is extreme boosting, and then you do the prediction. And this is how the prediction is being done. Now what I do is I kind of create a copy of the data, I drop the target variable, and then I try to do the prediction. And if you see the prediction here, it is very similar to what exactly the scale if you see in the real data, something like this. So let's say 463.26 and all. So if you go down here for the same data, you can see 14, so it's 463.9, and so let me, I can just do one thing. I can just kind of oh, sorry. So I can just kind of display df dot head. Let's see. Uh, so let's see the first three rows, and if you see, uh, probably will take, I don't know why it takes some time. Let, I think okay, I think because maybe it restarted. So 463.26, 444, and 488, and here if you go, here you can see, yeah, it came now, and you can see it's quite very accurate. 463.26, this is the prediction. 444, 444, and 486, quite very close. So that's all. This is the how I've solved this. Thanks a lot.